if I plot lambda versus E lambda B, okay. So essentially I am plotting 2h pi C naught square divided by lambda power 5 into exponential of h C naught by lambda k t minus 1, okay. So that is what I am plotting. So what I find is, for different temperatures, so that is the kind of behavior that you will get, okay. So this is as increasing temperature, okay. And this has been plotted for, it is very easy to plot this, just put a different temperature and plot it as a function of the wavelength. And so people have done this for the temperature of sun, okay, which is approximately 5800 Kelvin. And it turns out that the maxima, okay, maxima of that curve, it actually falls in the visible range, okay, it falls in the visible range, where we can see, right. Visible range is the wavelength at which we can see things, right. So in fact, the reason why we are able to get so much light from sun is because the maximum radiation that is emitted by sun, which is close to a black body, sun is supposed to be close to a black body. So the maximum emission that is radiated by sun, it falls in the visible range. That is why we are able to get so much light from the closest star, which is sun. Okay. So one can actually join these. So it turns out that, if I join it with a thicker line, so if I join all the maxima together, okay, at different temperatures, they all fall into a certain pattern, okay. So they all fall into a linear pattern, okay. That is the lambda max, which is the maximum intensity wavelength multiplied by temperature, okay. So that is a constant. In fact, I will show you how to derive this. It's about 2900 micrometer Kelvin, okay. So that is the sort of inverse linear relationship that actually one would find that the maximum wavelength as a function of temperature, it seems to remain a constant, okay. And in fact, it's not very difficult to show this. How do I find maxima of each of these curves? How do I find the maxima? You take the first derivative and set that to 0, right. So I have done that for you. So d by d lambda. So the way to see this is to express EB as in this form, C2 by lambda t minus 1, where C1 is 2 pi h C naught square and C2 is h C naught by k. So all we have done is just clubbed all the known constants into a single constant, okay. And then we find d by d lambda, EB lambda evaluated at lambda max equal to 0. So that is what will find you the relationship between lambda max and the corresponding temperature, and so that will be exponential of C2 by lambda Tm into C1 C2 lambda power minus 7 divided by Tm minus 5 C1 lambda power minus 6, that should be max, lambda max, okay, plus 5 C1 lambda max to the power of minus 6 equal to 0. So, if you take the derivative, that is what it will turn out to be, and after a little bit of algebra you can actually reduce the equation to this form: C1 C2 by 5 lambda Tm minus 1 plus 5 exponential of minus C2 by lambda Tm equal to 0. So, you can rewrite after a little bit of algebra, you can actually reduce it to this form, and now so you set x is C2 by lambda m t, okay, should be lambda m, okay, lambda m and Tm, where Tm corresponds to the corresponding temperature, and so you can solve the equation x by 5 minus 1 plus 5 times exponential of minus x equal to 0. So, this has to be solved numerically. So, you solve this, what you will find is that C2 by lambda m Tm is 4.965, and if you plug in the value of C2, you will find that lambda max into corresponding temperature max is about 2900 approximately, okay. So, you should actually solve this equation and try to find out the correct answer for that particular expression, and this is what is called Wien's displacement law, which relates the temperature at which the maximum intensity is achieved by a given black body, okay. Once again, a little bit of definition here. It's something called band emission, okay. So, this is useful particularly when you are solving problems, otherwise in my opinion I do not see much use for this band emission concept, but you should know this because it is useful in solving some problems in the exam, etc. So, what it tries to answer is to define a quantity called F, which is the fraction of emission, okay. So, supposing F 0 to lambda is basically the fraction of emission, fraction of total emission from a black body, okay. So, the total emission from black body is nothing but integral over all wavelengths, and f0 to lambda will tell you what is the fraction of the total that is emitted in that range, okay. So, simply from the definition 0 to lambda EB lambda divided by integral 0 to infinity d lambda, okay. What is the denominator? Integral EB lambda d lambda 0 to infinity, that is your Stephen Boltzmann law, right, sigma t power 4, right. So, that is nothing but 1 by sigma t power 4 integral 0 to lambda d lambda, okay. So, we can rewrite this expression in a slightly more convenient form, and that will be, so we change the variables, and that will be EB divided by sigma t power 4 into d lambda t. So, we just introduce a change of variables, okay. So, people have calculated this expression, and so you have the standard tables with x axis having lambda t and the y axis having 0 to lambda, okay. So it turns out that this is the kind of behavior. So it's particularly useful when you are doing certain calculations on Blackbody. So if you want to know what is the emission at a given range of lambda t, then you can simply find out using this curve here by subtracting the corresponding integrals. Okay. So if you want to know what is the emission in f lambda 1 to lambda 2, it is nothing but, what is this, f0 to lambda 2 minus f0 to lambda 1. Okay. So that will tell you what is the net emission in the range lambda 1 and lambda 2. So it's just a useful tool for solving some problems that you may get in your exam later. Okay. Otherwise, I don't see much use for the band emission concept, but I think it's just for, it's a useful tool. That's what you must understand. Okay. Any questions on this so far? Alright, so we have few more definitions before we really march into quantification of radiation process. Okay. Now the reason for such a definition is often you may not know what are the properties of a real surface. Okay. So remember when we defined Blackbody, we said that Blackbody is considered to be a standard, right? So you want to define all the properties of a real surface using the properties of the standard, which is the Blackbody radiation. Okay. So therefore it is useful to define a quantity called emissivity, which is represented as epsilon, and again it's a function of lambda and temperature, lambda, theta, phi and temperature. Okay. And it is essentially defined as the ratio of the intensity of emission from the real surface, which is again a function of phi, theta and temperature, with the corresponding emission from Blackbody. Okay. With the corresponding emission from Blackbody, which is not a function of the angular position, right? So this is essentially ratio of radiation emission or emission from real surface divided by emission from Blackbody at same temperature. That's very important. It has to be at the same temperature. It's a ratio of the emission from the real surface with that of the emission from a Blackbody, which is maintained at the same temperature. Okay. So similarly, one could define a spectral hemispherical emissivity. So the definition is a bit tricky. It's very different from what you would have seen a short while ago. So the spectral hemispherical emissivity, okay, is now a function of lambda and temperature. So that's the ratio of the spectral hemispherical emissivity of the real surface versus the spectral hemispherical emissive flux from the corresponding Blackbody, which is maintained at the same temperature. So it is not just the integral of the emissivity here. So the definition is emissivity is always defined as a ratio of the corresponding quantities. So here it is the ratio of the spectral hemispherical emissive flux from the real surface and the spectral hemispherical emissive flux from the Blackbody, which is maintained at the same temperature. Okay. So now we know what is the expression for E lambda E. What is it? It's integral of the numerator term there. So that will be, so I can rewrite this as okay. So epsilon lambda will be integral 0 to 2 pi, integral 0 to pi by 2, I lambda e, lambda comma theta comma phi comma t, all this sin theta, cos theta, d theta d phi divided by, what is E lambda b? Same, so it is nothing but pi I lambda b of lambda t. Okay. So we know that blackbody is a diffuse emitter, therefore I can simply integrate the sin theta cos theta and that will lead to a pi, there will be pi into I lambda comma b. Okay. So that is 1 by pi integral 0 to pi by 2, 2 pi 0 to pi by 2 I lambda e I could take this inside the integral because it is a diffuse emitter, and so it will be sin theta cos theta d theta d phi, and so that is 1 by pi by 2. This quantity, this ratio here is nothing but the emissivity, right. So that will be epsilon lambda comma lambda okay. So suddenly, because of the definition, you will see that there is a 1 by pi that has come in because of the definition. Okay. Unlike what we saw in emissive flux, spectral hemispherical emissive flux and the total flux, here you will suddenly see a 1 by pi that comes because of the definition of this ratio. So one can define what is called a total emissivity, that is epsilon, which is only a function of temperature. So that will be E of the real surface is a function of temperature, and E of the black body, which is only a function of temperature. So that will be integral 0 to infinity E lambda comma real surface into d lambda divided by what's the denominator term? Sigma t power 4. So epsilon t is 1 by sigma t power 4 into integral 0 to infinity E lambda d lambda. Okay. So the purpose of defining these quantities is, if I know the emissivity of a surface, there are ways to measure this. So if I know the emissivity of a surface, I am done, because I know how to characterize the black body radiation via the Planck's law, which is an exact equation. So from that I will know what is the emissivity from emission flux from a given surface. Similarly, if I know the spectral hemispherical emissivity, I am done. So if I know the local emissivity, I should be able to calculate the spectral hemispherical emissivity, because that is given by 1 by pi double integral the local emissivity, which is lambda e, into cos theta sin theta d theta. So if I know the local emissivity, I should be able to calculate the emissive flux, local emissive flux, spectral hemispherical emissive flux, and also the total emissive flux. Okay. So most of the real surfaces, in fact almost all the real surfaces, the properties that you will know is the emissivity of the surface, and in fact it is an intrinsic property. We will see a little bit about this in one of the future lectures, okay, why it is an intrinsic property, etc. Alright, so one could again define a similar quantity called absorptivity. One could define a quantity called absorptivity. So how do we define absorptivity? So note that we cannot use black body as a standard here, right, it absorbs everything. So what do we do? What is the net irradiation to the surface? And so the absorptivity is now defined based on the net irradiation that is received by a surface. So if we know how to quantify that, then we are done. So whatever fraction is received is what is called as absorptivity, and whatever is not received can either be transmitted or reflected. Okay. So we are going to, next class what we are going to do is, we are going to introduce saying that the net irradiation that is received is equal to the net irradiation that is absorbed plus reflected plus transmitted. Okay. So transmitted is in some cases, supposing if you have a translucent glass, okay. So there some of the radiation which is incident to the surface can actually be transmitted to the other end of the surface. Or if you have a liquid, for example, the radiation which is received on one surface of the container which is containing the liquid could actually be transmitted through the liquid to go into the other end, right. But if it is an opaque solid, then the transmittivity is 0. The amount of radiation that is transmitted is 0. So if it is opaque object, this is 0. So what we are going to start in the next lecture is by looking at a couple of more definitions. Very quickly we look at these definitions, and then we will start looking at how to quantify some of the aspects of radiation exchange and the emission from a given surface.